Alright, in this section we're going to take a look at graphing the other trig functions. We're going to begin with tan x, the tangent function, and we'll note that, to help us with this, we'll note that tangent of x is defined to be the quotient sine x divided by cosine x. One difference between tangent versus the sine and cosine is that the period of tangent is pi, not 2 pi. And rather than graphing tangent from 0 to pi, we'll graph it from negative pi over 2 to pi over 2 because we get a nice continuous curve when we graph it in that window. So I've started out by just providing values of tangent for some selected values of x from minus pi over 2 to pi over 2. The first thing you might notice here is that at negative pi over 2 we have a little star, and that's because tangent of negative pi over 2 is sine of negative pi over 2 divided by cosine of negative pi over 2. And cosine of negative pi over 2 is equal to 0. So we can't divide by 0. So tangent at negative pi over 2 is undefined. That's also true at pi over 2. In fact, anywhere that makes the cosine equal to 0, tangent is undefined. So let's plot these other points here. We're going to start off with the tan x using the values provided. And I provided the graph here already with the values marked out, except there's one error here. This says negative pi over 2. This should be negative pi over 4. So at negative pi over 3, we're at negative the square root of 3, which is approximately negative 1.73. All of these values we can get from the unit circle. We just have to do the division. Take the sine, which is the y-coordinate, and divide by cosine, which is the x-coordinate. I've just done that for us. So at negative 1.713, that's maybe about there. At negative pi over 4, we're at negative 1. At negative pi over 6, tangent is equal to negative 1 over root 3, which is approximately negative 0.577, so a little bit below half. At 0, tangent is equal to 0. At pi over 6, I just have the same values as I've already graphed, but positive, so that'll be a little bit more than half here. At pi over 4, we're going to be at 1. And at pi over 3, 1.73. So far, you know, if I draw a smooth curve that connects these points, you know, it looks something like this. Then the question still remains: well, what about beyond that? You know, what happens between negative pi over 3 and negative pi over 2, or between pi over 3 and pi over 2? And as we get closer to, say, pi over 2, right? So I'm gonna look over here. I'm getting closer to as x gets closer to pi over 2, cosine x gets closer and closer to 0, whereas sine x is just getting closer and closer to 1. So I'm taking values that are kind of leveling off at 1 in the numerator and dividing it by tiny, tiny numbers. And as you get closer and closer to division by 0, it makes your numbers blow up. You know, think about it. If I'm taking 1 and I divide it by a tenth, that's equal to 10. 1 divided by 1/1,000,000th is 1,000,000. So the closer that your denominator gets to 0, the bigger your values become. And so this just starts shooting upward towards infinity. On the other side here, we get the same scenario, only between negative pi over 3 and negative pi over 2, tangent is negative, so this blows up in the negative direction. These values at negative pi over 2 and pi over 2, we say that these are vertical asymptotes And a vertical asymptote represents a value of x that you're not allowed to plug into your function because it does something like divide by 0, which we're not allowed to do. And the behavior at those vertical asymptotes is such that it will make you either shoot up to infinity or shoot down toward negative infinity. So this is a graph of y equals tan x. Y equals 2 tan x. We're just going to take each of these values and multiply by 2. So this is still undefined, right? Wherever tan x is undefined, 2 times tan x is undefined. Here this is negative 2 root 3, and that is about, let me open up the calculator, about 3.46. And I'm just, that's a negative, and I'm just going to go down here where we have positive 2 root 3. Is positive, about positive 3.46. At negative pi over 4, we're going to multiply this by 2, so we get negative 2, and down here that'll be a positive 2. And then at negative pi over 6, we're at negative 2 over root 3, which is approximately 1.15. So negative 1.15, and the same thing down here. And 2 times 0 is still 0. So I'll do this one in blue. So at 0, we're still at 0. At negative pi over 6, we're at negative 1.15. Kind of like that. At negative pi over 4, we're at negative 2. And at negative pi over 3, we're at negative 3.46. So maybe about there. Oops. Didn't mean to do that. At 0, we're still at 0. At pi over 6, about 1.15. At pi over 4, we're at 2. At pi over 3, about 3.46. And then we can connect these. And we get the same behavior as x starts approaching negative pi over 2 and pi over 2. And if we do one more, I'll do this one in green, I think. 1/2 tan x, of course that's still going to be undefined there and there. This will be negative root 3 over 2, so I'm just taking these values and cutting them in half. And that's about 0.866, negative 0.866. Down here at positive pi over 3, we have positive root 3 over 2, which will be about positive 0.866. At pi over 4 and negative pi over 4, so tangent is 1 and negative 1, I'm going to cut those in half. So up here we get negative 1/2, down here I get 1/2. And then at pi over 6, it's 1 over root 3, so this, I'm going to multiply that by 1/2. So at positive pi over 6, we're at 1 over 2 root 3. At negative pi over 6, we're at negative 1 over 2 root 3. And that's about 0.289. So at positive pi over 6, a positive 0.289, negative pi over 6, a negative 0.289. And I'm just going to do my best. It doesn't have to be perfect, but I just want to kind of sketch this out, plot these points as best I can. At negative root 3 over, at negative pi over 3, we're at negative 0.866. So maybe about there. At negative pi over 4, we're at negative a half, then we're back to 0. Oh, I didn't mark down 0, but of course 1/2 of 0 is 0. And negative pi over 6, we're at negative 0.289, so maybe about there. At pi over 6, we're at positive 0.289. At pi over 4, we're at a half. At pi over 3, at 0.866. And then we get the same behavior as it approaches the vertical asymptote. So this is the basic shape of a tangent function. As I, change the number in front, the word amplitude probably doesn't really apply to a tangent function. Amplitude generally refers to how far you stray from that equilibrium, like reaching a maximum or minimum. And there is, as we can see, there is no maximum value or minimum value of tangent. It will attain all the values, all real numbers. But it does sort of affect how vertically kind of stretched it is, or vertically compressed it is. And we see that behavior change a lot in these sort of middle values. They all have the same behavior as you're getting close to the asymptotes. Sort of in the middle, you could sort of see that stretching, vertical stretching or compressing pretty clearly, or a little bit more clearly. So here we just graphed it from minus pi over 2 to pi over 2. But tangent, just like sine and cosine, is also periodic. So if I kept going, if I graphed it, if I included from pi over 2 to 3 pi over 2, I'd get the same shape, just repeated. So if you punch it in the calculator or something like that, you'll get just this same shape over and over again. And we can sort of see the period, sort of the distance between one point in the function and its repeated point in the next period. So it does have a period length of pi. Now cotangent, we're not going to fill out a table for cotan, but the process is the same. You could fill out a table for cotangent, just like we did with tangent. Cotangent is the reciprocal of tangent, so it's cosine over sine. And tangent had a vertical asymptote whenever cosine was equal to 0, because that's what we were dividing by. So that's why we had a vertical asymptote at pi over 2 and 3 pi over 2 and negative pi over 2. With cotangent, cotangent is cosine divided by sine, and so we get a vertical asymptote wherever sine is equal to 0, and sine x is 0 and at pi and at 2 pi, right? All the multiples of pi. We get a similar behavior, right? The similar kind of basic shape of the graph. And then just the asymptotes happen at different values. Because when we sketch a curve, a periodic curve, we want to sketch, usually when we sketch it, we'd say, I'm just going to sketch one period of it, but we'd like it to be a smooth, continuous curve. And that's why with tangent, when we graph one period of it, we pick, this one kind of in the middle from minus pi over 2 to pi over 2. With cotan, the period is also pi, but to sketch one smooth continuous curve, we sketch it from 0 to pi. We can change period and phase shift with tangent and cotangent, just like we did with sine and cosine, and we do the same thing, right? So whatever this coefficient is, that's what so the regular period of tangent is pi. And if I have a coefficient in front of x, the period of that function is pi over b. So we do the same thing that we did with sine and cosine, only it's pi over b instead of 2 pi over b. And to get the phase shift, we do the same thing. We're going to factor that b out, and then this number here is the phase shift. And again, it's to the left if we're adding it, it's to the right if we're subtracting it. The same is true for cotan. Here I've written it out for tan, but the same is true for the cotangent function. Let's sketch a graph of y equals tangent of 2x minus pi over 4. I'm going to begin. I can tell that there is a phase shift, and I'm going to begin by factoring out that 2, x minus, and let's see, this will be pi over 8, because 2 times pi over 8 is pi over 4. So having factored out the 2 makes it easier for me to discern what the phase shift is. The period is 2 pi over 2, because this is b. b is equal to 2. Sorry, not 2 pi over 2, pi over 2. Right, the period of tangent, tan of x is pi, so the period of tangent of 2x is pi over 2. The period is the phase shift, which I'm going to abbreviate as just PS, is pi over 8, and we're subtracting pi over 8, so that means it's going to the right. Alright, so just like we did with the sine and cosine, I'm going to start by sketching a graph of tan of 2x with no phase shift, and then I'll move things over. So the period is 2 pi, and with tangent, the middle happens at 0, and then I go from, I want to get a full period on by taking half a period on each side. So to get a period of 2 pi, I'm going to go minus pi over 4, pi over 4. These will be my vertical asymptotes for tangent of 2x. The coefficient in front of tangent here is 1, so even though we're not using the word amplitude, I still mark that value or observe that value, because at the halfway point to each of these asymptotes is where it's going to take on the value of 1. And that it's going to take on the value of 1 because that's a 1 in front. Halfway would be pi over 8. So that's a 1. That's a negative 1. And then, so I know that as it approaches the asymptotes, it's going to shoot up to infinity or down to negative infinity. It's going to move through these points in that kind of smooth curve behavior that we noticed in the other examples. So this right here is tangent of 2x. Now what I want is tangent of 2x minus pi over 4. I want to include this phase shift of pi over 8 to the right. So again, I'm going to take each of these sort of anchor points and move it, shift it pi over 8 units to the right. So this is going to move here. This will move here. Also, my vertical asymptotes are going to move. So let's see, pi over 8 units to the right means this value here will be pi over 4 plus pi over 8. That's 2 pi over 4 plus pi over, 2 pi over 8 plus pi over 8 is 3 pi over 8. And so there's my new vertical asymptote. This point moves over there. Here's my new asymptote. And there's the graph of tangent of 2x minus pi over 4. Okay. Let's do one more. We're going to sketch a graph of 2 times cotan of x over 2. Notice that there's no phase shift now. I can tell because we're not adding or subtracting a constant inside the function. The period, let's see, the value of b, the coefficient on x here is 1/2, right? This is 2 times cotan of, dividing x by 2 is the same as multiplying it by 1/2. So there's 2 times cotan of 1/2 x. So the period is pi divided by 1/2, which is pi times 2, or 2 pi. And now when we sketch a graph of cotan, we sketch it from 0 out to the end of its period. Right, because we're going to remember that cotan of x over 2 is cosine x over 2 divided by sine of x over 2. And so we're going to get a vertical asymptote wherever sine of x over 2 is 0. That happens at 0, and it happens at 2 pi, because if x is 2 pi, x over 2 is equal to pi, and sine of pi is 0. Halfway there is pi, and then I'm going to mark off quarters, pi over 2, 3 pi over 2. So cotan has the similar shape as tangent. At the halfway mark it's at 0, and at pi over 2 it'll achieve this value 2. So we don't call it the amplitude, but it still kind of marks an important anchor. You can convince yourself of that. Cotan of pi over 2 is sorry, pi over 2. That's when x is pi over 2. That means that x over 2 is in fact pi over 4. So cotan of pi over 4 is cosine pi over 4 over sine pi over 4. You might recall that pi over 4 is where sine and cosine are equal. So this is equal to 1, and so then when I multiply it by 2, this coefficient of 2 out front, it's going to hit that value of 2. Then it hits at pi, we're at 0. At 3 pi over 2, it's at negative 2. And so we get this behavior here. Similar shape, just kind of going the other way. And there's 2 times cotan of 1/2 x. Okay, so now let's talk about the secant and cosecant functions. The first step in graphing the secant or cosecant function is just to graph the corresponding reciprocal function. Remember that secant of x is 1 over cosine x, and that cosecant of x is 1 over sine x. So what you do is you graph the reciprocal function, the corresponding function, that's what I do. I always actually graph it, maybe lightly, because that's not the actual graph we're after. But places where that graph is 0 tells me where I'm going to be having a vertical asymptote, because we cannot divide by 0. And then we kind of plot out, use the behavior of either the cosine or sine function to tell us what the behavior of the secant or cosecant function will be. So let's begin. Let's say we're going to do cosecant of x, right? So the first thing I'm going to do is plot sine of x, and I'm going to make sure I leave myself plenty of space above and below. I don't want to take up the whole y-axis with the amplitude of sine, because I'm going to need space. It's got a period of 2 pi. Okay, so sine starts at 0, and then it goes up from there. Okay, so now anywhere where the sine of x is 0, I'm going to get a vertical asymptote. So I'm going to sketch those in. Now, sine of x is equal, where sine of x is equal to 1 at pi over 2, cosecant is also 1. It's 1 over 1. So there's that value. Now, as sine decreases, now imagine I'm gonna let x move from pi over 2 out to 0, okay? So now I'm taking 1 and I'm dividing it by things that are getting closer and closer to 0. That means this is going to increase. This is going to get bigger and bigger and approach infinity. The same thing happens as I let x go from pi over 2 to pi. I'm taking 1 and I'm dividing it by values that are getting closer and closer to 0, so this is going to shoot upward towards infinity. We get the same behavior happening between pi and 2 pi at 3 pi over 2. Cosecant is equal to 1, it's 1 over 1. And then as I let x get closer to values where sine is approaching 0, I'm dividing by 0, or getting close to dividing by 0, so the curve shoots, in this case, downward, because its sine is negative on that interval, so cosecant will be negative on that interval. So this, the gray is just sine. The graph that we're after is these two kind of disconnected U-shapes. That is the graph of cosecant, one period of cosecant. Now we'll do a graph of secant x. So we're not putting in any difference in period or phase shift right now. But if I had any phase shift or period, I would just sketch whatever that cosine or sine curve is with the phase shifting and period, and then draw in those U-shapes where they belong. So let's do this secant x. Cosine x, we know, has a period of 2 pi. So I'm going to mark that off. Got an amplitude of 1. I'm going to leave space on either side. I don't want to take up the whole y-axis with the amplitude of cosine. And cosine starts at its peak. And then it moves to 0, and then its minimum, 0, and then back to its maximum. So here's the cosine curve. And wherever cosine is 0, that's where I'm going to have these vertical asymptotes. And then we draw in those U-shapes. So I could tell, like, if we look between pi over 2 and 3 pi over 2, so in this middle piece here, right, it's a little bit easier to tell, and actually I probably should have done that in gray, so I'm going to fix that real quick. Okay, so in between, from pi over 2 to 3 pi over 2, I could tell that, you know, cosine, a secant will be -1 because I have 1 over -1. And then as cosine gets closer to 0, as I get close to dividing by 0, it's going to shoot downwards to infinity. Cosine is negative on that interval, so secant is also negative. And then over on the left, from 0 to pi over 2, at 0 I know it's 1, and then it's going to shoot upward towards infinity. Between pi over 2 and 3 pi over 2, I get this behavior. And it looks similar, a little bit different from the secant, but if I imagined, you know, kind of continuing the cosine curve like this, I'd have another asymptote here. Right, and then you'd see, like, you'd have these continuous connected U-shapes as well. Alright, so let's do one more. We're going to graph 2 times secant of 4x. The first thing I'm going to do is I'm going to start with y equals 2 times cosine of 4x. I'm going to graph the associated reciprocal function. The amplitude here is 2. The period is 2 pi over 4, or pi over 2. And I'm just going to start off this problem as though it's just a graphing a cosine problem. So my period, I'm going to go out to pi over 2. Means this is pi over 4. So this is pi over 8. 1 pi over 8, 2 pi over 8, 3 pi over 8 here. My amplitude is 2. I'm going to be careful not to take up the whole y-axis with the amplitude. I'm going to graph now cosine of 4x. So my anchor points here, it starts at the maximum down to 0. Here's the min, back to 0, back to the max. Oops. I'm going to draw in my asymptotes where cosine is equal to 0. And then I draw in my u-shapes where they go. So that would be here, here, here. So the graph of secant is just the black part, right? These u-shapes. But I'm using the graph of cosine, which we did in gray here, to help that sketch, to help me see what it should look like. And that's basically how we do the secant and cosecant graphs.